Welcome to the second video on Chapter 5 Probability for the Year 12 bit of the A-level course. So the previous lesson we looked at Venn diagrams, and today we're going to do much of the same thing. The main difference here is we're going to introduce the concepts of mutual exclusivity and independence, and what that means in the context of Venn diagrams. So let's get started with 4 warm-up questions. So if you have a look at these, jot them down if you don't have the notes, and attempt these in your own time independently. When you're ready to see the answers, press play, and I'll show you how you could arrive at the solutions to these. Okay, so I hope you've had enough time to have a go at them. Let's have a look now at question number 1. So question 1, we've got 2 events A and B such that the probability of A is 0.3, the probability of B is 0.4, and the probability that we have A and B, the probability of the intersection, is 0.12. We're asked to draw a Venn diagram to show this information. So a couple of things to notice here with this one. The first thing to notice is there's only 2 events, A and B, and there is an intersection. So we need a Venn diagram with 2 regions and an intersection for those regions. So we could begin by sketching out something like this. So a rectangle including all the sample space, then A and B with an overlapping section. So we need to draw and complete this diagram. So as ever, always start with the overlapping parts, the intersections. So this bit here, the intersection, relates to this bit in the middle. So we're told what the probability of an event lying in the intersection is. We're told that's 0.12. And so what we can do here is just add in the value 0.12 to this section. So in other words, we just added this in. Next, we can go forward and work out the probability of A. Well, the probability of it lying in event A is 0.3. 0.12 is already part of this A circle, so we need to think about what else we need to add on to 0.12 to get to 0.3, and that would be 0.18. And the B circle, the event B, has a probability of 0.4. We've got 0.12 already, so 0.4 minus 0.12 would be 0.28. A common mistake at this stage is to think we're done, but we always need to remember if there's any value which is neither A nor B. Doesn't need to be a value represented on the rim of this rectangle. So as you should know from GCSE, the sum of all the probabilities for any event should add to 1. These don't, so that's how we work out the number on the outside. So we're going to do 1 subtract all these numbers. So at this point, get your class whiz up and ready to go. I'm going to do 1 minus 0.18 minus 0.12. Whoops, press plus because I'm silly. And then minus 0.28. And that gives us 0.42. So on the outside of this Venn diagram, we just label somewhere on the outside 0.42. And that's all we need to do. And we've done question 1. Warm-up question 2, we have a tree diagram to complete. A little heads up, tree diagrams are going to form the basis of the next lesson. Not here, but the next lesson. So let's have a look how this is labelled. So we've got A here, which represents event A. A dashed means the complement of event A. A dashed means not A. So if the chance of A happening is 0.3, the chance of it not happening must be 0.7. Up here we've got the chance of B happening is 0.4, so the chance of B not happening, the complement of B, must be 0.6. We're not told any other information, so we can assume that these probabilities are unchanged. So up here we can do 0.4 and 0.6 again for B and B dashed respectively. Part B says find the probability that events A or B happen. So this is where we need to go along these branches and multiply as we go. And so the probability of A and then B is 0.3 times 0.4. So this one's going to be 0.12. This one, 0.3 multiplied by 0.6, that's going to give us 0.18. Down here, 0.7 multiplied by 0.4, that'll give us 0.28. And finally, 0.7 multiplied by 0.6 would give us 0.42. The magic of this, all these final values will always add up to 1. If they don't, a mistake must have been made. So we want to work out the probability now that A or B happens. And so the only way that can't be the case is this last branch. The only way A or B, or some combination of A or B, can't happen is if not A happens and then not B happens as well. And so this one here, the probability of A or B must just be 1 minus the probability of not A and not B. If A and B don't happen, and we subtract that probability, the only option that's left is there's some A or some B. So it's 1 minus this 0.42 and 1 minus this 0.42. If you want to try on your calculator or otherwise, it's 0.58. Another way you could have done it would have been just to add up these three numbers together, because these three numbers I'm highlighting in red include at least one of A or one of B. So that's a different way of doing it. I'm just showing you how to do it using 1 minus the complement of A unified with B. Question 3, some triangle talk. So we've got this triangle ABC and we've got this information about it. Now with these questions, we're told the lengths of the sides of a triangle, but you're not given any diagram of a triangle. I'd always recommend to just sketch out a triangle yourself. So we've got AB, which is 10, side AC is 7, and an angle at A of theta. So let's just draw in a triangle first of all to make it come to life. So let's label what we've got here. So AB is 10, AC is 7, so this one from A to C is 7, and the angle at A, middle letter rule, is theta. Now from earlier, using the lessons from trigonometry and triangles, you should remember the formula for the area of the triangle. So the area of the triangle ABC, area, is going to be half AB sine C, where A, B, and C are just arbitrary letters. The main thing here is you can see that A and B have nothing to do with C. And so our A, this is the formula, so A or B are just either side of the angle. So in any order, A and B have to be the two sides that encompass the angle, the two sides surrounding the angle. And C, in this case it's angle A, I know, but how we label it is arbitrary as long as you know how to apply it. Our C here always has to be the angle in between the two known sides. And so our C, if you like, is this theta. So using the information we've got, we know the area is 21. So 21 equals a half times 7 times 10 times sine theta, because c is theta. So half times 7 times 10, that's going to be 35. So 21 equals 35 sine theta. Now if you read this question carefully, you can see we don't actually need to find theta. We're just trying to find sine theta. So if we just divide both sides here by 35, we'll get sine theta is 21 minus 35. In other words, sine theta is 0.6. If you're wondering whether sound has just got slightly better, all of a sudden, I'd stupidly forgot to plug my mic in. So it was the laptop recording, so it wasn't as good, so apologies for that. But hopefully now it'll be less grating on your ears. Anyhow, sine theta is 0.6, and so that's question 3 sorted and done. Next question. Use your value to question 3 to find the 2 possible values of cos theta. So we need to remind ourselves of what question 3 was. So from question 3 we had sine theta is 3/5. Now it might be tempting here to try and do a cast diagram from what you've seen from the trigonometry sections, but we need to try and remember a relation between sine and cos theta. It's a really important relation which is crucial for year 12 and year 13. Do you remember a relation? Well, here it is. It's sine squared theta plus cos squared theta is the same as 1 in every single circumstance. So all we need to do here is plug in sine theta. So what I'm saying here is sine squared theta, which is sine theta all squared, plus cos squared theta equals 1. Now 3/5 all squared is 9/25. So we have 9/25 plus cos squared theta equals 1. If we then subtract 9/25 from both sides, we get 1 minus 9/25, which is 16/25. Then if we square root both sides, and remember to do plus or minus on this side, we see that cos theta is going to be plus or minus root 16 over 25. So that's going to be minus 0.8 or 0.8. Essentially 4/5 or minus 4/5. So you can leave it as decimals or fractions, it's completely up to you. So minus 4/5 and plus 4/5, or minus 0.8 and plus 0.8. Now let's return to Venn diagrams and do these in a bit more depth, following on from last lesson. So mutually exclusive and independent events. So what are they? Well, when events have no outcomes in common at all, they're called mutually exclusive. Mutually exclusive means they can't happen at the same time. A common example of this is if you flip a coin, heads or tails. It can't be happening a head and a tail at the same time. It's one or the other. They can never happen together. So there's a test of mutual exclusivity. So to test if an event is, 2 events rather, are mutually exclusive, the probability of A or B will always be the probability of A plus the probability of B. So in the example I just mentioned, heads or tails, heads and tails are mutually exclusive, so chance of a head or a tail is a half, so head or a tail is certainty, so 1 equals half for a head plus half for a tails. So that is just a very quick example of how it works in reality. So if 2 events can't happen at the same time, how could we represent 2 mutually exclusive events on a Venn diagram? Well, if it can't happen at the same time, there's never any overlapping section, because it can never be A and B. So you need 2 regions for both A and B, and they mustn't overlap. So we're looking at something like this. So an event space for A and a space for B with no overlap whatsoever. Now, Separate to mutually exclusive, this is a different concept I'm talking about now. When events can have outcomes in common, but one outcome does not affect the other, then these events are called independent. So therefore, if A and B are independent, the probability of A happening does not change the likelihood of whether or not B happens. So for example, rolling a dice and flipping a coin. You could have heads and a 6 happening at the same time, but if you flip a head on a coin, that's going to have no bearing of if you rolled a 6 or not. So one doesn't affect the other, but you can have a heads being flipped and a 6 rolled on the dice at the same time. So a test for if two events are independent is this. The probability of A and B is probability of A multiplied by the probability of B. If the probability of A and B doesn't equal this, then the two events are not independent. In other words, the events would be dependent. Similar here, if this relationship doesn't hold, then that's a proof that two events are not mutually exclusive. So we need to have in our minds very clearly these two. Mutually exclusive, this adding rule. Independence, this multiplication rule. Let's have a look at an example. So let's imagine choosing coloured counters from a bag, that old example which has been used time and time again. So let's have a look at case 1. Let's imagine the events are independent. So this bag here has 4 red counters, 2 blue counters and 1 yellow. So 2 counters are chosen at random from the bag with replacement. So once they've been taken out, they're put back in for the second drawing. So illustrate this information on a tree diagram. So if we had this, what's the chance of picking a red one? Well, we've got 4 red counters, and in total, we've got 4 red, 2 blue, and 1 yellow. So that's 7 counters in total. So the chance of picking a red would be 4 out of 7. That means the chance of not picking a red, the complement of picking a red, would be 3 out of 7. So these branches represent the first picking. For the second picking, we're told that the counters are put back. And so what happens in the first pick does not affect the probabilities for the second pick. So the first picking is independent of the second and vice versa. So because the counters are put back after the first picking, there's the same number of counters as before, hence the same probabilities. So for this one, the chance of picking a second red would again be 4 out of 7. The same down here as well. Hence the chance of not picking a red again would still be 3 out of 7. So that's the case if the two events are independent of one another, if one doesn't affect the other. However, what would happen if we didn't replace these counters? In that case, the first picking would affect the numbers of counters and the types of counters for the second picking. So the probability of the second pick would be affected by what's happened the first time around. So let's have a look at that now. So what if they're not independent? So similar setup to before, but this time 2 counters are chosen without being replaced. So let's illustrate this information. So first of all, at the very start, we still have these same 7 counters. 4 out of 7 would be red, and 3 out of 7 would not be red. So let's have a look at this first scenario here. So imagine we took the upper route and a red one's been picked. It's not been replaced, so after this stage, there's 6 counters left. If the red one was picked and not replaced, that leaves us 3 reds left. So the chance of picking a second red would be 3 reds, 1 less than before, because 1 red here was picked and not replaced, out of 6, because there's 1 fewer counters in total. 7 take 1 gives us 6. Likewise down here, the chance of not picking a red would be 3 out of 6, so 50-50. Down here, let's imagine we picked something that wasn't a red. So we've picked either a yellow or a blue, essentially. So if that isn't replaced, again, there'd now be 6 counters left to choose from. The chance of picking a red, well, down here we picked a non-red, so we've still got all 4 reds remaining. So that would be 4 out of 6 down here. Therefore, the other 2 counters out of 6 would be either yellows or blues. So that shows how one depends on the other. They are not independent, which is the same as saying the second probabilities are dependent on the first. Let's have a look at some worked examples now. So here, we've got 2 events A and B, which are mutually exclusive. So before we continue even reading, mutually exclusive, that's the key thing. So we've got 2 events, A and B, and we're told they are mutually exclusive. So this is absolutely key. So there's only 2 events, so we need 2 curved regions. Because they're mutually exclusive, they don't need to overlap. So we can now actually just draw out the Venn diagram template. So it should look something like this. Now we can fill in the rest of the information. So we're told that the probability of event A is 0.3. And so this goes here. And the probability of event B is 0.1. So that goes in the B circle. However, as ever, always remember that the sum of all probabilities always adds up to 1. So 0.3 plus 0.1 gives us 0.4. That tells us on the outside we need 0.6. So now we can proceed. So for part B, it says what's the probability of A and B? So in other words, this is saying what's the probability of A intersecting with B? It's one and the same thing. So here I'm just using the notation just to remind you how the language links to the mathematical notation. So here, because there's no overlap, there's 0 chance of A and B happening together. It's the same as knowing that they're mutually exclusive. If you know they're mutually exclusive, A and B can never happen together. Part B, A or B. So because they're mutually exclusive, we can apply the law for mutually exclusive events. The probability of A or B is the probability of A plus the probability of B. And so that just equals 0.3 for A plus 0.1 for B. 0.3 plus 0.1 gives us 0.4. For C, A but not B. So the probability of A happening but not B well, if A happens, because they're mutually exclusive, B would never be happening anyway. So that's the same as saying A happening but not B. That's just the same as A happening. A can't happen with B. So this here, by saying but not B, that's just really obvious. It can't be B anyway, because there's no overlap. So the probability of A but not B is the same as just the probability of A itself, which is just 0.3. And finally, D, probability of neither A nor B is this 0.6. So that's how it works with a fairly simple example. Let's have a look at a couple of harder ones. So question 2, we've got a Venn diagram showing the number of students in a particular class who watch any of 3 popular TV programs. So we're asked to find the probability that a student chosen at random watches B or C or both. So A, probability of watching B or C or both that's the same as working out the probability that a student falls in the union of B or C. So we need to work out here how many students there are in total. So this total diagram, we've got 3 plus 4 plus 5 plus 10 plus 7 plus 1. So the total number of students in this case is 30. Double check on your calculator if you'd want to, but there should be 30 students here. So B or C or both, like I've said, that's the same as saying what's the probability of a student being in the union of B and C. So the union is all of the B circle as well as all of this C circle. So all we need to do here is to total up the numbers in each of these 2 bits. So what you might want to do actually instead is notice, well, that's everything apart from this 3 and 1. So it's everything apart from 4 students. So that's going to be 26 students I've called in. So it's going to be 26 out of 30. Which again, if you really want to, if you want to, it's optional, you can simplify it down to 13 over 15. Whereas B, we need to determine if watching A and watching B are statistically independent. So for this one, we need to work out what the case is if they're statistically independent. So we need to remember the formulas from before. The main formula I'm talking about is if the events are statistically dependent. So if 2 events are statistically independent, then we can say the probability of A and B, the probability of the intersection, should equal the products of the separate probabilities. So it should equal the probability of A multiplied by the probability of B. So in the intersection, what we've got here is the overlap of A and B is 4. So we can now say the probability of A and B is these 4 students out of 30. Whereas PA times PB needs to be the same as 4 over 30 if it simplifies. So PA, everything in A is this 3 plus 4, which is 7. So probability of being A is 7 students out of 30, multiplied by PB. B has 19 students. So the probability of a student liking show B is 4 plus 5 plus 10, which is 19 out of the 30 students. And so if we calculate this now, so 7 over 30 multiplied by 19 over 30, we get 133 over 900. So we can now see from these two that they're not equal. 4 over 30 isn't the same as 133 over 900. Okay, if it was, they'd simplify to the same thing, and they clearly don't. So probability of A and B does not equal PA times PB. So for that reason, A and B are not independent. If this had equaled 4 over 30 or 2/15, they would be independent, but because it doesn't, that shows that they are not independent of each other. So in practical terms, it might be that B and C are two fairly similar programs. So for example, if someone likes watching X Factor, they might also have a tendency to watch another reality TV show or something like that. So A and B are not independent of each other. Let's have a look at the final worked example now. So here we've got again some students, Alfred, Bianca and Chris. And just by sheer luck, their initials are A, B and C, which makes things very easy for us. Anyway, they're sometimes late for college. The events A, B and C are as follows. So A represents the event of Alfred being late, B represents Bianca being late, and C represents Chris being late. We've got this Venn diagram here, showing the events A, B and C, and the probabilities associated with each region of B only. So only B's been filled in. The constants P, Q and R represent probabilities associated with the three separate regions outside of B. For part A, we have to write down two of the events, A, B and C, that are mutually exclusive. Give a reason for your answer. At this point, you need to recall that mutually exclusive means cannot happen at the same time. And how will that look on a Venn diagram? It's events A and C that are mutually exclusive. And if you see here, it's because their regions don't overlap. Circle A and circle C in no way overlap or touch. For that reason, we can see A and C are mutually exclusive. Let's have a look at part B next. We're told that the probability that Chris is late for school is 0.2. I'll come to that second, but what I want to look at here is this sentence here, that the events A and B are independent. So find the values of P, Q and R. Well, if A and B are independent, we can use the law of independence for probability. So A and B are independent, therefore what we can deduce is that the probability of A and B is the probability of A multiplied by the probability of B. In terms of the regions on the Venn diagram and the intersection, it's the same as saying this. The probability of an event being in the intersection is the same as the probability of A multiplied by the probability of B. So the intersection of A and B, we can see here, is this 0.12. Because 0.12 lies in the intersection region of A and B. And so what this means is, because they are independent, the probability of A is going to equal, probability of A multiplied by probability of B will equal this 0.12. So we can now formulate an equation. So 0.12 equals a probability of A. The probability of A is P plus this 0.12. So P plus 0.12 multiplied by the probability of B. Now B, we've got 0.2, this 0.12, and 0.08. So if you add all of this together, that gives us a probability of B, which is 0.4. The grand sum of B is 0.4. So now you can see here we need to expand this out. So 0.12 equals P times 0.4, which is 0.4P, plus 0.12 multiplied by 0.4, which is 0.048. Next, rearrange, so we've got the values on one side and 0.4p on its own. So 0.4p equals 0.12 minus 0.048. So 0.12 minus 0.048 gives us 0.072. Therefore, divide through by 0.4. P is going to be 0.072 divided by 0.4, which is 9 over 50, which is a decimal, is 0.18. So P is 0.18. Now we can do the easier ones. So we're told here that the chance of Chris being late for school is 0.2. So 0.08 plus Q equals 0.2. So a really simple rearrangement. Q is going to be 0.2 minus 0.08. Q is going to be 0.12. Then finally R, the bit on the outside, will just be 1 minus all these other probabilities. And so R is going to be 1 minus P, so 1 minus 0.18, minus 0.12, minus 0.2, minus 0.08, minus Q, which we just calculated as 0.12. So if we just do this quickly with our class whiz, but not so quickly we'd make a mistake by rushing it. 1 minus 0.18, minus 0.12, minus 0.2, minus 0.08, minus 0.12 again. That gives us 0.3. So R is 0.3. So we can now add this information on to the Venn diagram. So we can replace P, Q and R at this stage with the actual values they represent. So now using these values, adding them in, we're better placed to tackle part C. Part C says state whether or not B and C are independent, giving a reason for your answer. Well, using the independence rule, big if, because you've not proved it yet, if B and C are independent, the probability of B and C will be the probability of B multiplied by the probability of C. So what we need to do here is think about what B and C means. B and C represents the intersection. Okay, so we have a look where B and C intersect, essentially where they overlap. So we've got here 0.08, as you can see. So if they are independent, then PB times BC should equal 0.08. So probability of B and C is 0.08. And PB times PC. Well, PB, probability of B, are these three numbers added together, because 0.12, 0.2 and 0.8 are all in this circle, and they all add up to 0.4. And the probability of C in this C circle, we've got 0.08 and 0.12. Add those two together, we get 0.2. And 0.4 times 0.2 equals 0.08. So we can now see that probability of B and C, B intersection with C, does equal the probability of B multiplied by the probability of C, because 0.08 is the value of each of them. So therefore, that proves that B and C are independent. Let's have a look at the final part now, using this result from part C. Part D, it says to comment on the teacher's belief in the light of your answer to part C. Well, the teacher's belief, just going back to the wording on your notes, the teacher's belief is that when Chris is late, Bianca tends to be late as well. And so it would seem that he's sort of hinting or insinuating that when Chris is late, Bianca is as well. So maybe they're going to school together, or they're maybe boyfriend and girlfriend or something. So he's trying to say there's some relationship between their latenesses. Whereas actually what we prove for part C is that if they are late or not, one's lateness is independent of the other. And so that would seem to say that actually the teacher's belief is likely to be incorrect, since B and C are independent events. So this means that Bianca being late has nothing to do at all if Chris is late or not. So I say here the teacher's belief is likely to be incorrect. It's very likely to be incorrect, but there is a possibility of just by freak chance they happen to be late on similar days. So they could be late by sheer coincidence, but if they are late on the same days, it isn't because one person is affecting the other in any way. It will only be through coincidence. But obviously, it's very unlikely that you have multiple coincidences again and again. That's why it is likely that the teacher's belief is incorrect. Bianca's and Chris's lateness has nothing to do with each other. And I want you to try some questions on your own. So it starts at page 77, exercise 5C. Try all the questions from 5C on the Stats and Mechanics book for year 12. So by now you know the drill. Try the questions independently. Double check your answers using the books. If your answer is wrong, let me know, or use the model solutions to give you a helping hand. If I'm not around, I'm always here on an email or even in the comments section of the video. Thanks for watching the video. Do please subscribe, and I'll see you soon, hopefully in the next lesson. Okay, bye for now, and take care.